Okay, so my name is John Paragreen, and I'm the project manager of the NeTIRail-INFRA project. So just a quick overview of the project. The NeTIRail-INFRA project was developed with the concept of tailoring technology for particular lines. So understanding that the technology that might be used for a busy high-speed railway will be very different technology to what is optimum for a lesser used, maybe rural line. So throughout the project, we were looking at, as I say, tailoring solutions to the different types of railway lines. But one of the things that is particularly important is to maintain interoperability. So this is so that you can open up the potential for some of the lesser used lines to also be used as diversionary routes. So for example, you can see that where you maybe have a rural line that links two cities, you could ultimately use that line as a diversionary route to this high speed or highly utilised track. So just a little bit of a summary of the NeTIRail-INFRA project. NeTIRail-INFRA is a 5.4 million euros project sponsored through INEA, part of the European Commission, and part of their Horizon 2020 programme. The project includes 13 partners from 8 different countries, and you can see on the slide those countries and companies listed. So in terms of the way that the project is structured, we had 7 different work packages. Now, 3 of those were particularly technical work packages. So work package 2, looking particularly at track infrastructure technology. Work package 3, looking at tailored powered infrastructure. And work package 4, which you will hear a lot more about today, looking at monitoring and smart technology. Now, one of the things that is quite unique about the NeTIRail-INFRA project is also the focus that we had in the project on looking at the business case and market needs for different technologies, but especially also looking at the societal perspective. So thinking back to especially the rural lines that we've considered in this project, they may not have particularly good economic viability, but in many cases they connect communities to large cities. They're important for people commuting to jobs, and therefore they have a large societal benefit. So within this project, it was particularly important that we consider the societal perspective. We also had a work package 6, which has developed some evaluation and decision support tools. These tools, what's happened within work package 6 is that a web-based application has been developed, which I will show you a screenshot later. It's GIS based, but it's designed to allow infrastructure managers to gather data on a GIS basis in order to help support their decision making. Okay. So just going through some of the NeTIRail-INFRA outputs. So within work package 2, for example, there's been a lot of modelling of rail corrugation to try and understand the fundamental causes of corrugation. We've also looked at transition zone design and how we can develop low-cost solutions to transition zones. Within work package 3, we've developed some low-cost monitoring and smart technology for looking at overhead power lines, particularly understanding the dynamics of the overhead line. And this has been complemented by some modelling, where we've looked at low-cost catenary systems, particularly looking at a simplified trolley wire system. And again, that system has been modelled in order to understand the constraints around its use. And then I won't talk about the low-cost monitoring and smart technology for track, because that's what everybody else will be talking about later within this session. And so also, this is just a screenshot of the web-based GIS tool. If you are interested in the GIS web tool, we have another demonstration online at 2 p.m. today, so 3:30 today. So if you want to find out more about the GIS tool, then please join the webinar that we have this afternoon, and you can find details of it either on the NeTIRail Twitter feed or from our website. Okay, so that's my brief introduction. I will now pass over to Alfredo, who is the work package leader for work package 4. Alfredo will start off by giving us a little bit of an overview and introduction into work package 4, and then we'll go into more depth about the individual technologies. So, okay, Alfredo, I think at the moment your microphone is muted. Okay, there you are.
Okay, now can you hear me, John?
Yes.
All right, so thank you for the introduction, John. My name is Alfredo Núñez. I'm a researcher at the section of railway engineering of TU Delft, and I'm going to talk to you about the measurement campaigns that we perform in the framework of the NeTIRail-INFRA project in Romania. There were 2 tests, one in Foreu test ring and the other in the line Bartolomeu-Sarnesti. Then, let me see. Okay. So the content of this presentation will include first an introduction of what is axle box acceleration, and then 2 results, one for the Foreu testing ring, from which a whole test ring was tested and defects were detected, mainly wheel burns, and measurements were conducted at different speeds. And the other application was, the other measurement was in the railway line near Brasov. And then some defects and validations are going to be discussed. So first of all, what's axle box acceleration? It's a measurement system that consists of accelerometers that are mounted on the axle box of the trains. Then, whenever a wheel is passing over a defect, like the ones that you see over here in the pictures, so a small indentation here of squat A, or a larger one like this one with already some cracks over there, then the wheel reacts differently as if it were passing by a smooth rail. Then with the acceleration systems, then we can detect those changes, and with the positioning, we can assess where the defects are located and how severe they are. So far, we have conducted extensive measurements in the Netherlands, and in the picture here below, you can see our measurement coach that we use also to connect with industry so that the different partners can test their technologies in the Netherlands in the TU Delft measurement train. But then during the NeTIRail-INFRA project, we wanted to prove generalization of this technology, and then we have tested the measurements in Romania, in Foreu and Bartolomeu-Sarnesti, and here you can see the trains, the locos, and the wagons that were used for it. Here you can see one example of the signals. So over here you see a small defect. In this column, you see the measurements at the right rail. At the right, over here, of the presentation, you can see the measurements then at the left rail. And you see vertical and longitudinal measurements. And then you can see then that for this defect, both vertical and longitudinal accelerations, they are excited. And then we can detect this little defect. The principal effect, you can see that for a small defect is mainly on the longitudinal direction. Over here, you see other defect. This is a more severe squat. In this case, you see over here the left signals. That means that this defect was mainly located at the left rail. So here you see all the left signals, and here you can see the vertical acceleration signal and the longitudinal acceleration signal. In this case, the vertical is more important, and you see over here below also the wavelet power spectrum with the frequency content of this signal. So by making use of this information, then we can detect and assess the severity of the defects. So that's the technology. Now I'm going to show you the measurements that have been conducted in the NeTIRail project. Over here, you see the whole team of people that were involved in the measurement campaign. So from TU Delft, from the AFER, the company there that is in charge of this testing ring. And those measurements were conducted in October 2017. The test ring looks like this. So over here you see a big ring. This test has been used for assessment of trains at a high speed, up to 200 kilometers per hour, 220. And because of the type of measurements and testing that are conducted, you need to guarantee that the track quality also for the test ring is in a very high standard. Then we detect the defects, and in the right part you see what are the principal variations of the ABA energy that were located in the measurement campaign. Over here you see some examples. With D, we refer to small defects. S and C are the switches and crossings. They also can be monitored by using this technology, especially the crossing. And IG are local insulated joints. W are welds that somehow they inform that there were very high energy, very high dynamic forces happening there. So those welds that were detected here are relevant for being monitored. Then over here, I wanted to share one video. This is how the measurement looks like when you are on the loco. And, here. Over here, you can see the speed of the loco. So in this moment, then we are running around 200 kilometers per hour and going even further. And yeah, that's the beautiful view that you can get from the testing ring. Over here, you're gonna see how it looks like when looking from the track side. So over there, it's passing by very quick. So yeah, the collection of information is it's while the train is passing by at that speed. It's a very quick measurements covering the whole infrastructure very fast. So here's some examples of the defects that were detected. Over here you see those wheel burns. Now, just for showing a few examples, in this case, one of those defects that I showed you before are located here at the position 0 of the diagram. Here you see the right and left vertical acceleration, and over here the right and left longitudinal acceleration. The responses over here, because the track is in a very good condition and those defects were quite localized, then you clearly see that there's something going on that piece of rail by looking at the time domain signal. And over here you can see also the frequency wavelet power spectrum, which you can also assess the frequency content. Because as you see here, for instance, the track, of course, is continuing continuously vibrating, and somehow those vibration will be related to another frequency bands, then you need to focus into the bands, the frequencies that are related to defects. So this is at 80 kilometers per hour. The defects can be detected even at lower speeds. And over here you see the responses at 200 kilometers per hour. Here, although it was a very small defect, you see over here why it's necessary to have higher standards for the rail condition when you're using high-speed trains. In this case, it's 200 kilometers per hour. It's a very fast going train. And the dynamic effects can be quite high, even though you have a very small local defect. From this picture, then, we can see that this ABA system works quite well at higher speeds. And the higher the speed gets, the more clear are the responses. Next, I would like to show you the results from the measurement conducted in Bartolomeo Sarnesti. Those measurements were done on September 2016 in partnership with with our partners from NeTIRail project and RCCF. In this case, the measurement was implemented in a passenger train, and the passenger train was actually in operation. And over there, you can see a cyclist jumping into the train. And with this measurement, then we could see that the ABA measurement doesn't need really a measurement train to be conducted. You can actually mount the measurements into passenger trains, and the concept of a train can be extended to not just transport people, but also to collect information about infrastructure, to know about the quality of the rails, to know about the quality of the welds, the switches, the transition zones, and all the different assets that you have for here in the track. Over here, the train is passing by over a bridge. So also over there, we had a very beautiful view. And here is just a video while the train was collecting the measurements. So it was not as high a speed as in Fareo test ring, but still here we had other conditions because those railway tracks were actually quite heavily used. They were in operation. So the challenges are a bit different. Also, this railway line is let's say it's a line that is quite used for the passengers living here in this area. So it's quite important for them. And over here we can see the challenges for making use of the data. There are over here you see a plot of the speed versus the distance. This is in meters, so it means that we have around 25 kilometers of track that were monitored. Over here you see the signals of the speed of the trains. And as you can see, there are some areas where the train reaches a maximum speed, but there's quite high variability. In some moments the train has to stop, of course, because you reach an station, and in that moment we cannot get information from the signals when the speed is very, very low. From the measurements conducted in Fareo, we could get information in around 20 kilometers per hour, which is the lowest. But then if the train is not moving, then yeah, we will not get information about the impact over the defects. Also GPS accuracy, because this was a regional area, and somehow the accuracy was not as high as what we could reach in the Netherlands. So also here there's a variance and some difficulties for positioning, although from the main defects, we provide the location to the partners and they verified that for all the locations, there were something going on in the track. And also there are many other challenges for this kind of data. And some of them were handled in other work packages, like in the work package 5 for societal benefit, because this railway line is very important for the people living over there to connect to Brasov and for to avoid people jumping off into vehicles. Over here, it's the map of the highest energy variations that we found with the measurement train. 75 of them were verified by the partners and RCCF, and they find out that for each of them there was something going on in the track, and then they can conduct further monitoring and to take care of those locations. So it's not just about the most important dynamic forces, but also we can detect all sort of defects. One of them, corrugation that you see over here. So this is a corrugation in this line. It's not really short pitch corrugation. It has a wavelength that is a big bigger than the larger than the short pitch, and then this can be measured and by making use on the longitudinal acceleration. It looks very clear where the corrugation is located. That's the energy signal that you see here below in the graph. We also conducted some validations with current welds. In this case, if you see on top of the welds or in the side, they all look similar, but however, they all have different dynamic effects. And those measurements and those effects, we can capture them by the loading condition of the train passing over them. Over here, you see the three plots, weld number 3, weld number 7, weld number 11. From the time domain signal, the first weld has a higher peak, that is around 60. The weld number 7, it's around 50. And the weld 11 is around the maximum peak, around 40. So here is, if you look at the energy signals, then for defects, then you can do actually a ranking of which weld is more relevant for possible maintenance. And that kind of information is not, you cannot do it by visiting the welds. So that's a very detailed information and could be relevant for maintenance plans in the future. Over here, I wanted to show you some results about a multi-objective optimization that we conducted for this line. Here we generate trade-off between maintenance operation, number of replacements, that is the J2 function, and the impact on performance. And that's considering the energy levels for defects. That's the objective function J1. And we tested different multi-objective optimization algorithms. And over here, you see the trade-off curves. In J2 is the number of replacements, and in J1 is the performance of the track. So, of course, as you increase the number of replacements, it's going to get you, for maintenance, a higher cost. And then you can see here how much your performance will get. In this case, decrease means that it gets much better. So over here, then, by fixing, for instance, a maintenance budget, then you can detect, like, okay, right now we can replace 1 or 2 or 3 pieces of track, but making use of the ranking, you can decide which part actually to do. Over here, you see the locations for when conducting 25 replacements. So in the course over here, when we fix this number at 25, then for each of the algorithms, we get different locations that should be replaced. Some of those locations are quite similar to each other here, around kilometer 15 to 20, but depending on the algorithm, sometimes other locations are also triggered. And over here you see, for one example, so we have here the 25 locations, and over here you see the more detailed part. You can rank which one is the most important location in terms of the performance. So some conclusions. In the Netherlands and Romania, the detection of defects with different severity was possible. And with the NeTIRail project, we could prove the generalization capabilities of ABA, meaning that we can also prove this technology in other countries. Detailed information of the defects can be used to optimize the grinding plans. This is because we can detect very small defects, and if you find clusters of them, those areas of defects, before they evolve into larger defects with cracks, then the small defects, they can effectively be removed by the grinding plan. So you can fit the grinding depth and to totally remove those defects, and they will not reappear again. Also, in the case of moderate and severe defects, they are detected, and we can also provide a ranking of them. So the replacement operations for those defects can be focused into where's the most important. From the Fareo testing ring, the measurements were conducted and responses obtained at welds, switches and crossing joints, and at both the conventional speed and at high speed. In this case, we tested from low speed till high, from 20 up to 220 kilometers. For all the speeds, we managed to detect the defects to assess their severity. So the system then becomes suitable for metro, conventional lines, and high-speed railways. Also, with the measurements obtained in the testing ring, we can fit responses curves based on the speed of the train that will help to make full use of information coming from passenger trains. Because in passenger trains, we have high variations of speed. In this case, then with what we obtain from Fareo, we can fit curves that get adapted to the different conditions of the passenger trains and to make full use of the information we are collecting, no matter what speed we are running. Finally, the measurement was conducted with passenger trains, and this information provides with the most relevant locations for field inspections. The further research is going to focus on light detection of defects, also on self-learning algorithms for inspection of infrastructure. And here, we don't claim that with this technology you must replace the current measurement trains. No. Here with this technology, what we say is that it is possible to massively collect information about the railways with current passenger trains on the run, and later make use of that information to fuse it together with other sources coming, for instance, from image processing, ultrasonic, eddy current, and with all that information you have a global picture, a more complete, coherent picture of what's going on in the railway track. So that's it. Thank you all for your attention.
Okay, thank you very much, Alfredo. Does anybody have any questions for Alfredo? If you want to ask any questions, you can use the chat function, the tool. But if not, if we move on to the next presenter, which is Vlasta. Are you okay, Vlasta?
Okay.
So I return to being presenter. And Vlasta is going to present the dynamic measurements which were carried out in Slovenia. Okay, Vlasta. Okay.
Mouse.
Yeah, oh, there is another mouse here. I don't know if it will reach. Are you okay to use it?
Can I use? Oh, great.
Or you can use it.
Mm-hmm. Hello. My name is Vlasta. I'm coming from Slovenian Railways, and I will represent dynamic measurements in Slovenia. My presentation will be first about what measuring technologies we use in Slovenia, and then more about dynamic measurements that we make. I will speak about technology, equipment, and then correlation with geometric and corrugation measurements, and at the end some words for conclusion. In Slovenia, For track monitoring, we use high resolution, more precise measuring trains. And beside measuring trains, we use portable measuring equipment as well, which is used on each standard vehicle. In this picture below, you can see one Hungarian measuring train which we hire for geometric measurements. I will speak quite a lot about geometric measurements in Slovenia. So we use a lot of monitoring technologies, like measuring geometric parameters, which are stability, direction, cant, twist. We make rail diagnostics, such as ultrasonic control, rail wear, corrugation, and eddy current. And the next one is with portable equipment on standard vehicles, and these are measurements of dynamic track parameters like lateral and vertical acceleration. And of course, beside trains, we make also visual inspections. Let's go to dynamics. Dynamic measurements are carried out by portable measuring equipment, which contains sensors mounted on a bogie of a passenger train, and they're connected with measuring system inside the train. These measurements need preparations like calibration and installation of the equipment. And beside that, we also have to establish a setup measuring file. With dynamic measurements, we measure lateral and vertical acceleration with more sensors, and then average lateral and vertical accelerations is calculated. And beside acceleration, the kilometer position of a train is measured in order to find out which place is for that vibration that we detect. The equipment for dynamic measurements, we use two types of accelerometers. First one is low frequency accelerometers made by Devesoft company, and they have a frequency range 80 Hz. The other type is high frequency accelerometers made by Dytran company, and they have much higher frequency response from 0 till 2500 Hz. I have to say that these type of accelerometers, well, this one, were financed within NeTIRail project, and with them we got the opportunity to research the difference in detection between different frequencies of vibration. And in this picture below is some comparison or both graphs together. This is vertical acceleration, and the difference between both types is mostly in the amplitude of the signal. In these two pictures, you can see how these two types of sensors look like. Above is low frequency, and the new high frequency ones are on the picture below. Here, this picture show both, well, all sensors installed together on the bogie of a train um, under the cabin of a train, and a lot of cables is you can see, and these cables are connected with the measuring system inside the train. And in this picture on the right side, you can see how these cables are connected on the back side of a measuring system. And now let's go on to the comparison of dynamic measurements. First, with geometric measurements. Geometric parameters are like direction, cant, stability, twist. And in the next slide, you will see this comparison, and you will see circles, how these different parameters are connected or correlated. The lateral acceleration is correlated with direction and cant, and vertical acceleration is related with stability and twist. Yes, twist and stability. Here, the red ellipses show correlation of lateral acceleration, and the blue ellipses show correlation of vertical acceleration. And now here I have some more examples. This, I have to apologize, is not so good resolution, but this picture you can see in the deliverable 4.4. 4.4 is track and ride quality monitoring technology based on train-borne measurements in standard vehicles. Here we made comparison between dynamic and geometric parameters. In this picture, you can see black lines, and these black lines illustrate correlation of lateral acceleration above. This is the first graph first graph on this picture, and is mostly related with this green direction. And the second graph is vertical acceleration, and it is mostly related with yellow stability. And in this picture is also seen that these higher energy peaks appear mostly in curves of a track. And another example from the same deliverable 4.4, as you see on the right side, vertical and lateral acceleration are reversed, because lateral acceleration is first graph and vertical is second one. But the correlation is the same. Red lateral acceleration is mostly related with green direction, and blue cant. Blue, I mean the second blue below. And of course, the second graph in this picture for lateral acceleration is mostly related with yellow stability, and as well with brown twist. And what I can also say is that you can see as well that the shape of these graphs are very similar. Shape of lateral acceleration, direction, and longitudinal profile of a track, which you can see totally at the bottom of this picture. And similar with here, also longitudinal profile below, and the same here. Longitudinal profile has the same shape of a track, the same as lateral acceleration and direction. Now let's go to corrugation. With this new high frequency accelerometers, we tried to research the correlation I don't know, to prove some more usability of this equipment. In this picture, you can see green and red ellipses, which again show correlation with dynamic parameters. And we found out that, of course, vertical acceleration is correlated with stability, and green circled corrugation is correlated with larger difference in vertical acceleration between high and low frequency sensors. But this statement needs some more research. You will see later. Here, on this picture, we have connected corrugation graphs above on this picture, which are related with higher difference between low and high vertical acceleration. And of course, as explained within geometric parameters, vertical acceleration is mostly related with stability. And again, everything appears mostly in curves of a track. Here in this picture, well, perhaps this one gave us the idea that dynamic measurements are connected with the difference in vertical acceleration between different frequency sensors, because where the corrugation is most dense, the most density of corrugation appear at the same place as the higher difference in vertical acceleration between high and low sensors. And now I want to say something for the conclusion. We can say that a correlation between dynamic and geometric parameters has quite high or big reliability. But on the other hand, correlation between dynamic, vertical parameters and corrugation is not so pronounced. In this case, sensors should be placed closer to the formation of the corrugation. If it is so, then the correlation is more reliable. Within NeTIRail project, we tried to prove that dynamic measuring equipment is usable, and we proved that the potential usability of dynamic measuring equipment for early diagnostics, such as such as detecting poor places or poor places more higher, higher energy peaks appear on these places if you see the graphs. Early diagnostics finds out where failures on the track can appear in near future. But this statement need some more research. We should test also different sensors, and we have to improve this system, and then the equipment we really can really be usable. Thank you very much.
Okay, thank you. Thank you very much, Vlasta. Okay, thank you, Vlasta. Does anybody have any questions for Vlasta? As I say, if you have any questions, you can raise them in the chat bar within the GoToMeeting software, or you can enable your microphone and ask them directly. However, I will now pass you over to Lucian from ADS, who will present the work on developing low-cost smartphone applications for looking at comfort monitoring. Okay, thank you, Lucian. I can see your screen.
Thank you. Do you hear me?
Yes, we can hear you.
Okay. Hi, I'm Lucian. I'm working ADS Electronics, and I was a task leader into the task 4.3. In my presentation, I will try to present the goals of this task, system architecture of the application, standard and models for evaluation ride comfort, layout and functionality of the smartphone application, and also the test results into the test line Bartolomeu Zărnești. Our goal into the development smartphone application was to create an application in order to collect information by GPS sensor and accelerometer by the smartphone, and also to send this information to a data center using mobile network, and another application in order to see the collected information into the graphical format. In fact, our application are contain 6 modules. The 3 modules are into the mobile application. Here we have an communication services in order to transmit the data to data center. We have an local databases. We have an location services, and also vibration circuitry. Into the control center, we have a service for collecting information. This information are stored into the database, and this information are displayed into the application. For development of our application, we are trying to collect information in order to identify the perception and reaction of state of physical condition in vehicle environment, such as dynamic, ambient, and spatial variables. For interpret this data, we are used ISO standard 2631. In this standard, the information was structured into the non-uncomfortable, a little uncomfortable, very uncomfortable, uncomfortable, very uncomfortable, and extremely uncomfortable. All these perceptions are according with the acceleration, acceleration of vibration. So the comfort are in generally caused by vehicle speed, track quantity, radius, count, leg transition curve. Vehicle quantity is the vehicle characteristics like suspension, vehicle body, seat, and all these create an perception of comfort received by the user. Our application was developed using a standard layout in order to be easier to use by the user. We don't need any special knowledge of IT or skill in use the smartphone application. During the development, we are taking into consideration the manageability. For example, here you can see the chart. For this chart, the user have ability to scroll up, down, or zooming for different zoom. Also, we have an intuitive menu in order to start the monitor, to see the log, and also for settings different variables using into the application. My interface of mobile application display in real time the GPS position. For example, here, if this button is green, we have position by the GPS. If it's yellow, is by the network. Also, we have undescripted information in order to see the accuracy of location. In real time, we have the latitude and longitude, and also the speed provided by the GPS, and also the vibration in three directions, by X, Y, and Z. This information is provided by the accelerometer. Another feature is the calibrate. The calibrate is really useful in order to eliminate the noise vibration, for example, the engine. This button, when push this button until the start recording, we can calibrate, and all the noise are eliminated by the signals. Also, the mobile application provide two types of log. One log is related to vibration. In this log, we can monitor vibration and filtering the vibration along the three axes. And also, we have another logs for comfort. In this log, we can see into the graphical, the comfort, and also roll and pitch acceleration. Here is a short demo. I will try to start. A short video of the application. After start to the application appear this information. We can settings the URL with data center for consuming the web services in order to transmit the data in real time to data center. Also, we set credentials for consuming these web services. After we set the information related to the rail unit and the route along to monitor in order to identify and analyze the specific registration. And also we have possibility to set a threshold of value provided by of accelerometer according to ISO standards. Because the data provided into the standard is more than 10,000 registration per second, we can filter this information in order to recording only the specific value. So now we record some information, and now we can navigate into the log, and we can see the graphic into the graphic format, the acceleration. We can zooming and moving along the interface for the specific point. For example, here we reduce the zoom in order to see. We can, for a specific point, we can see the maximum value for each Y or Z vibration. Also, for the comfort, we have a similar interface, but here we can see the comfort value according to standards and also roll and pitch. Moreover, the plotting are offer a feature for filter in order to display all together information or one by one or other combination of this value. So the application, the mobile application is really easy to use, and we was use this application into the 3 locations for testing. One testing was into the Turkey, one testing was into the Slovenia, and 2 testing was into Romania, one into the Faurei ring, and was into the Bartolomeu Sărnești, because into Bartolomeu Sărnești is the passenger traffic lines, and it also is a secondary lines. For this testing, we are mount the smartphone. The smartphone you can see here into. You can see here into the cabin of driver, and we'll recording the all information along Brașov and Zărnești. After collecting this information, we are plotting many different geographic information into the GIS application. For the railway, for the Bartolomeu Sărnești route, we are storing the geometry of the track line, the contour and the station position, the contour of level crossing position, and also for each switch and crossings. After performing the measurement over the full track of Bartolomeu Sărnești, we are detect a potential defect along the line. All these defects are plotting with the red along the line, and for detect this potential defect, we are taking into consideration the largest energy variation of highlight, the largest energy vibration of collected by accelerometer. Also, we have a possibility to plot the speed records of along all the road. This is important because this information can provide us information regarding to the consumption results by the railway caused by the mode of driving. For example, here we can see a bad style of driving, because with the intense green is the high speed is more than 65 km/h, and with the low green we can see a low speed. Normally, this speed here is necessary to have a progressive acceleration, because we are start by the line, and into the middle normally we have a high speed, and near the next station is necessary to speed lowest. But here we can see, here we have a high speed, and here we have also high speed. In the middle we have a low speed. It's not a good driving style, and this style increase the consumption of diesel. Other information plotting into the GIS application is the roll and pitch. Here we have a P by rotational along the Z axis, and down we have the theta. This is the lateral acceleration. Another, in this slide, we present the acceleration along the all three direction X, Y, and Z, with different green is by X direction, is different blue is by Y direction, and with red is in Z direction. During our testings, we are trying to identify a pattern for identify a potential defects, and the good results is because we have a similar patterns for each point detection. For example, here we have into the point number 145,331, and here is for another point. Into the same, for example, here for comfort, we have a similar pattern into the height vibration. For acceleration, we have a similar patterns, and also for roll and pitch, we have a similar pattern. Into the right is the different position for of this point along the Bartolomeu Zărnești track line. As conclusion, using this application, we can estimate the cost saving into nice and renewal resulting from the application, because by analyzing the vibration in times coupled with the speed of travel and at the rail units, the possible effect of the suspension system can be identified more quickly than in case of the visual inspection. Also, analyzing the comparison between running speed records, the fuel consumption can be reduced by adjusting the drive mode without affect the scheduled time. Analyzing the velocity data coupled with location provided by GPS, we can identify the failure in the track geometry. Aspect cannot be done through the periodical visual times. As benefits, because we monitor especially the passenger comfort, we can increase the attractiveness of railway travel by increase the comfort. Also, by track monitoring, our application increased availability of status of track extension, because it eliminates the need to inspect time to set a check to the route. This is relevant, including the assessment in capacity is well used during the part of the day. And now I will show you the possibility into the GIS map for filtering. For example, here we have a track route Bartolomeu Zărnești without information, just with switch and crossing. This is the thing for switch and crossings, the level crossing, and with yellow is the station. For example, for monitor, when I plot, the information are collected by the databases. And appear the information regarding the different point with problems. Also, we can see the speed in parallel with this for example, here with different colors. It's the plotting of speed in different colors. The same, we can see the velocity information. Also, we can see the vibration along the x-axis, and we can filter, display more information or others, depend of necessity. The same is for Y and Z. So we can conclude that using the smartphone application for monitoring the track, we can reduce the cost for maintenance, because using this application we can eliminate small part of visual inspection, and also the most important is because we have an images of the comfort of passenger. The owner can intervene to make an correctness of the rail units or of the track, depending of the cause can make the discomfort of the passengers. So thank you, and if you have a question, I'm here to respond.
Thank you very much, Lucian. Has anybody got a question? Does anybody have any questions about the smartphone app? I think otherwise we can move on to Tudor's presentation.
Yeah,
but
just a second.
But if anybody does have any questions, you can raise it in the chat section on the GoToMeeting app. So we can always respond to that later if you do want to ask a question.
Hey, John, I might have a question.
Yes, of course.
Yes, I'm.
Yes. So for the mobile technology, that's also a way to connect the infra manager with the actual passengers. Is it also possible to enhance even more the experience of the passengers? Because right now they're going to be collecting information for the track, but maybe also some information about their own feeling or their own experience about riding the train. I don't know if it's too crowded or if they are arriving late. It's a kind of information that from the passenger perspective maybe could also be useful for the infra manager.
The application is more useful for the owner of rail stock of the track manager, because the track manager of or rail units owner can have an information into the real time according the perception, and can correct the different mistake along the time.
Okay.
For the passenger exit, another application developed where don't intend to have an application for travel user.
Okay.
We are intent to make more visible secondary line on other line and reduce the cost with using a low cost application.
Okay, so is it yeah, Lucian, is it possible to use the same framework? So as Alfredo was asking, you have created databases where information can be transmitted from the mobile phone into databases for use by the infrastructure managers. Could it also be used to pass other data to the infrastructure managers? So, for example, if a passenger wanted to use a mobile phone app to say this train is overcrowded, could the app be modified to allow a passenger to have that functionality?
Yes, it's possible.
Okay.
To access the application and also to send directly to the manager, because the mobile application have own databases, and by settings to send this information to endpoint, this information are sent directly minute by minute.
Okay, perfect. Okay, thank you very much.
You're welcome. Thank you.
So if we can pass over to Tudor.
Yes.
Okay, thank you, Tudor.
Okay. My name is Tudor Popa. I'm working at ADS, Electronic Research, and in this project, I was actually still I am work package leader for work package 3. So first presentation, we want to propose to make working together two systems designed and developed in the project. We designed and developing the project two systems related to collecting acceleration data. Both systems are from different work packages, different tasks, different work packages. But at the end of the project, after test, we consider a big improvement if we'll see in the next presentation. It's very easy to integrate both systems in one big system, integrated system, because we consider could be a big improvement. And the presentation will show common points for achieving this goal. We integrate two systems from NeTIRail, from two different packages in one big integrated system. So again, first system was named Acceleration Monitoring System for Overhead Contact Line. It's part of work package 3. And the second system is named Acceleration Monitoring System for Plain Line and Switching Crossing, part of work package 4. Both systems passed in real field test, and we consider could be claimed the TRL6 as development level. So about vibrations for the both systems, they are as a common point. They the vibration, the acceleration are in the lower spectrum for both. This type of lower spectrum of acceleration will cause resilience, decreasing resilience of the contact line, for the contact line connecting with other components when they're fastened, like clamps, like joints between contact wires. And also, this is the differences. For contact line will register large amplitude of vibration. Is different by the acceleration on the range. So this large amplitude of vibration will cause on the contact line fatigue cracks in the section of wires and clamps and the other fastening points. Vibrations in the railway track, lower spectrum also, but they are provide some phenomenon different phenomena. So the energy from the wheels and the rails produce noise with airborne propagation and ground propagation. So these are very negative effects against adjacent buildings sensitive to the noise, like medical buildings, like technological buildings, and I don't know, military buildings. So these are similarities and differences between vibration for both systems. So this is the presentation of what means one system acceleration for a contact line. It's here in the left up, consisting the system from. Yes. Okay. Christian want to show me an improvement of arrow. So the system for monitoring acceleration of the contact line consisting from sensors placed on the groove of the contact line, concentrator device, and the long-range communication device to send the data to a control center. Here, it's the system for rail track. It's almost the same, differing only the placement of the sensors. They are on the foot of the rails. And other components, other devices are the same. So why do not send to the same concentrator device, do not send information also from sensor on the contact line, but also from the sensors on the rail. They can use the same frequency, they can use the same area, and all to send to the control to the concentrator send information. Also, the terminal interface are similarly, actually, are almost identically. So in the left we saw the interface, terminal interface for a contact line, and here are the terminal interface for the rail. The main functions for both terminals are to receive data, to show data in real time, and also to save in CSV format. Maybe here could be data received from different types of sensors could be spread in two files, to be separated for post-process analysis. So, an improvement could be saved data in two files, two CSV files. But the terminal interface is the same. Its functions and aspect. About experiments for overhead contact line, we perform two levels of tests more than other systems. One level, first level was as laboratory extended experiment. We will provide here description of test on USFP specialized laboratory, and after that, the second stage, real field condition. We made only one session of experiments in real field conditions because of hard conditions for installing a system. We'll see in the presentation. For railway track test, we achieved tests in many many places. Brasov, our partner SCCF, in Turkey, and after Faurei. These are official tests because we made many other unofficial tests to make working the system. So, few advantages of using the system. I'm talking about now the integrated system. Objectives are almost the same for both: to collect acceleration data for long time and continuous mode. One system from the contact point, and the second for the railway track level. Because it was a main requirement from the project, because long time monitoring acceleration values provide information about wearing degree through comparing historical data. For example, after installation could be taken a first set of measurements, and this could be considered as better. And all other measurements in time, weeks, months, even years, could be compared with this pattern because the sensors are in the same place. The condition, the rate, and the infrastructure are the same. Could be compared, and in this kind could be detected, could be determined the wearing degree. Knowing the next step, knowing wearing degree, will help for changing. It's one of the most important objective on the entire project. Will help to change the planning maintenance on regular time, on fixed time, to the on-demand strategy. So the strategy could become when is needed and where is needed. As another requirement was for the systems to be in the low-cost category. So for this objective, we have no other way than we designed and developed the systems from the integrated circuits level. So we not paid any module manufactured by other companies. We made all from the integrated circuit level. Also, other advantages are common for both systems. Could be detected very fast critical defects and taken measures for new designs, also for new designs and for models. Knowing long time historical data could help for creating or maybe optimizing new models for new designs, also for contact line, but also for rails. After experiments, we can say the sensors could be placed also in many other locations to take vibration, to take acceleration from any other component. For example, for overhead line components like droppers, catenary wires, isolators, and for rail components, sensors could be placed also on the sleepers, on the clamps, joints, etc. As very shortly, novelty technical characteristics, it's wireless communication. So non-invasive as no wires for data transmission. Actually, for contact line taking acceleration, it is not possible to put wire. Also, total autonomy in terms of power supply. We experiment this and it's working using batteries and photovoltaic cells. Another novelty, we use accelerometer circuit as digital with many functions inside. So the accelerometer provides us in the same time, I don't know, it's nanosecond, provide all values for all three axes in the same time. Also, environment functioning should be taken into consideration. About settings for test for both systems. Here are a few differences. For example, the common point is for all cases, for all sensors, 400 samples per second. Even this sampling rate could be increased. The sensor accept over the 5,000 samples per second. This another setting. It's about acceleration scale. Are different here. For example, for overhead line, we set it for test interval range as 4G. For the rails, we set it two types of case. 4G for rails with concrete sleepers, and 8G for wooden sleepers. We see why. We set it also because accelerometer support this are integrated many functions and release our microcontroller from some functions provided by the integrated circuit. We set it for collecting data and stopping collecting data at restful level, about 2.5G. It's changeable. we choose this. We chosen this. And also another function of the firmware, we have to, from test, we have to let the train pass that area to send with less errors to send data. So we have to, considering this threshold level, we save data inside the memory of the microcontroller, and when train is passed, we send data having open air of communication. Yes, another common point we tried to make for all registration for both systems was the list of functions for post-processing. So we have here to have possibility to compare data, to compare registration. We had a list with amplitude of acceleration, also acceleration amplitude for details. For a short time, we can see here the shape of acceleration, more clear than here. And also another function about distribution for acceleration values. That means how number of acceleration from one value are collected. Also, most important are the spectrum. We provide in our analysis the spectrum for displacement, double integrated acceleration, into two scales. One for seeing most important components, is it is a scale, linear scale, and also logarithmic scale to see smaller values for high frequency. For displacement spectrum in these two scales, and for energy. So these are the functions follow for all registrations for overhead contact line monitoring acceleration and track rails acceleration. First experiments was for overhead line, was achieved in the laboratory of the USFD. The USFD laboratory provided inside one installation specialized for producing accelerated querying of the contact line. So they sent contact force in different frequencies, in different values. Contact force produced displacement of the contact line, and our sensor placed in different points could see the results, could see the effect of that program of making displacement with frequencies and amplitude. Yes, post-processing compares of what was generated by the actuator with data received by sensor. So two images about placement of sensors. For example, here are all three sensors placed on the contact line. But we want to see how much components from the energy are lost in the other components of that installation. So we put sensors also on the actuator pole here, like here. Were generated many programs with high and low frequencies, pulses, singular pulses, to see the response in the frequency domain of that discontinuities with different amplitudes, and we'll see after that, we'll see in parallel, in the same time, we'll show the results. So for example, here we have one example of low frequency generated contact force here. The contact force is generated for only one axis. The displacement is here, it's about 3 Hz, the frequency. The frequency is about 3 Hz. And post-processing functions, we received this type of acceleration in it's one example for one sensor here. We received this type of accelerations to this contact force string of pulses. Could be seen very easy here even the actuator provides for one axis values of contact force and displacement, the sensors make registration for all three axes. That means the energy is spread on all three axes, which is a good thing because in reality, this is happening. The contact force provides components for all three axes. Also, we made post-process functions, acceleration spectrum in real time, in neural time, also to see the shape. So the conclusion for this test on USFP laboratory, the actuator provides contact force, but sensors could see what's happening in the installation. And further, we think further improvements would be the sensor system, the accelerometer sensor system, could take from the real field data from different situations, like different trains, different power supply system, different speeds of trains, and coming back to the laboratory with these registrations could be provided, could be created programs related to this registration considered as pattern. So the programs for producing accelerated wearing of the contact line would be closer to the behavior, to the real behavior of the contact force. The second test for overhead line was the experiment at FFO rate. Only one, I say only one test because of hard conditions for installing the system. Three stages, three conditions was achieved for installation of the system. First, the power supply was interrupted for entire ring section. This is the most important thing, and was not possible for other railway networks, commercial railways network, because to take power and also to close the line many hours means a lot of lost in earnings. It's not possible to be to interrupt a commercial line few hours only for testing this system. After that specialized vehicle was brought to the sensor fixing location, two sensors were fixed in the groove of the contact line, and it's important to make correlation between the code of the sensor and the location where present. So we put one sensor approximately in the middle of the span and one sensor near the dropper to see if the dropper has attenuation functions of the contact force. This image is about fixing sensors. It's about placement of the sensor. Here, approximately in the middle of the span, is the sensor. It's the sensor code 2, yes, and code 1 is here near the dropper, but after the dropper, because the train running from here, from the right to the left, from code 2 again to code 1. Was recorded a list of speeds, and we see here one example which appearing us very interesting. So the code 2 before the dropper, it's here registering acceleration. It could be very easy to see. The sensor start to collect data about 1 second before reaching the pantograph, the contact point below the sensor. This is the point when pantograph reach the contact point. But code 1 near the dropper start to sense. It's about that threshold level. Start to sense the pantograph coming about 0.5 seconds. So it's obvious that the dropper has an attenuation quality, has attenuation characteristics of the acceleration produced by the pantograph. Also, the spectrum, the spectrum for code 2 and code 1 are in the same expected range. So the code 2 important values are about 0.2. That means 20 centimeters for z-axis, and for code 1 near the dropper, it's about 5 centimeters. So 20 related to 5 centimeters. Also for y-axis, we see here 0.1 above 0.1. Yes, that means above 10 centimeters displacement, and here are below 10 centimeters displacement. Also, conclusion: the droppers make attenuation of also displacement. But we saw something interesting here about energy, because here the energy for z-axis is in the same in the same logic. It's less, it's more displacement for z-axis before the dropper, and less energy after the dropper. So more energy before the dropper, less energy after the dropper, near the dropper. But for 0x and 0y, the situation is exactly the opposite. We can see here for y, for example, we can see here the value of energy is about below 0.05. I think it's 0.03 here, and here reaching 0.05. Also for x, it's about 0.01 before the dropper, and here it's about 0.03 near the dropper. So we have an hypothesis here, because the dropper make reflection of the propagation wave. So existing the reflection of the propagation, that means the longitudinal component of the contact force extended by the pantograph, which is part of this energy, it's reflected against the pantograph is coming. So both energies are cumulated, and that is what sensors receive. Accumulating energy from the past, that component reflected, and the energy from the present. It's a nice subject of study. Conclusion for overhead experiments was the most exciting, most concerning, not functioning this system, most dangerous, but the main benefit, I think, this system, actually this experiment on the contact, on real condition on the contact line, it's top of our system developed, because it's sure now microelectronics could work on that very high voltage, on that very high potential, 25 kilovolts for after power rate. So test related to the track. First test was in the winter. We put here 2 sensors in a switch and crossing area. Train speed was I try to hurry up this presentation. Train speed is under 50 kilometers per hour. It's important to see, to make comparing with the next test. The fastening solution was with clamps, mechanical clamps, because the gluing, double adhesive gluing was not possible, being low temperature, negative temperature here in that period. So we registered this type of acceleration. But important are to see the scale. Acceleration are about AG, plus minus AG. They are very high amplitude. Also displacement here, because in the next test in Turkey at PCBD, we met other conditions, different conditions related to the infrastructure, because our lucky was to make measurement also on that speed, on the same speed under 50 kilometers per hour, like on RCCS. But they have a very hard, very heavy rails, 60 kilograms per linear meter, and also concrete slipper, solid concrete slipper. So we make registration like this. Could see here, we consider that differences, concrete slippers and heavy rails, making these differences about acceleration. Could we see here are not reaching 4G here, then here about 8G, where they have RCCF has wooden slipper and some places rotten wooden slippers. So we can see here very low amplitude of accelerations because of infrastructure quality. Also, as a spectrum, the spectrum frequency are a bit higher than this is about 7-8 Hz here, are a bit higher than for RCCF, where are about 3-4-5 Hz, low difference. But that means the vibrations, because of concrete slippers, are a bit higher in the frequency. So the last experiment of track system of acceleration monitoring plane lines and switching crossings was the last experiment was after February in the March. We made measurement, a lot of measurement with many speeds. Measurements were achieved on 3 locations with special characteristics. One switch and crossing used as entry point, one insulating joint for track circuit, and one continuous line section. Also, the conditions, the line is very used, are in very good shape. They use maintenance all the time for that ring. We will present here the 90 kilometers an hour for the insulating joint location, because seems to be very interesting. So this is the location. We place the accelerometer. Could be see it's an insulating joint, but it's in a curved section here. So we have lucky to make measurements first time in a curved section and with rails at different levels. And we saw very interesting things about this. The measurement we presented here are for a speed of 90 kilometers an hour. The 2 rails are at different levels. Important to know the relation between code of sensors and the rails where they are placed. So code 1 is on the inner rail here, and code 2 is outer rail, higher. So we have this registration, which are very different. Code 1 is inner rail. That means a lot of vibrations with high density and the large time of registering. Then code 2 is outer rail. That means it's very easy to see the wheels pushes much more the code 1 inner and the lower rail. So in this intersection are very important to know the optimum speed. The optimum speed it's about when the wheels pushing equally the rails. So the rails could be in this optimum speed could be used equally. As conclusion, uneven pressing rate and transferring of uneven energy cause different wear degree. So for wearing, for equally wearing, need to be followed the optimal speed. But this optimal speed is very hard to find. here are also about displacement are very high here on the inner rail than outer rail for 0Z. For 0Z is not so a big difference, but for 0Z here it's about 0. It's about 5 centimeters. 5 centimeters for inner rail, and here are about 1 centimeter, so 5 times less on outer rail. For y-axis, also is important, is 10 times. It's above 5 centimeters here, displacement, and here it's a little more than 5 millimeters for the outer rail, so 5 times pushing more for inner rail. Considerations about using system interface was lucky again. Was lucky to us to see, to make experiments in this type of section, because the requirements for the system were to design a system for plain lines and switch and crossing. But it's also very useful, this system, for in-curve sections. Can detect differences very well. Some advantages of the system could help to found in time, because in time the optimal speed is changing, because it's changing the infrastructure quality. In time, the system could help to find again and again the optimal speed, which inform the driver, will help to make longer the life of the rails, and also to make the maintenance to be done for both rails, because if the rails are used differently, the maintenance should be made at different times for different rails in the same location. So, as solutions, as a conclusion for integrating the both systems we show, they are after developing stage, putting in function and experiments, we have a common list of technical specifications which create possibility of both systems to be integrated. So these systems are very easy to be integrated actually with no additional cost, because they are working on the same place, on the same frequency, and could send their data to the same concentrator. Maybe at the control center should be spread information in 2 databases or in 2 files, should be spread to make differences between information acceleration collected from the contact line and acceleration collected from the rail. So this was the presentation. Thank you for your attention.
Okay, thank you very much, Judah. Does anybody have any questions for Judah? No? Are you going to move on to your next presentation?
But we can show now something running.
That would be perfect.
It's time.
Yes.
Yes. We'll start the terminal interface application. First, we'll show some recorded data from the test, from the experiment. We have a playback function, and after that, I will try to start the system to collect data from our sensors here in the laboratory.
Okay, perfect.
We have time?
Yes, yes.
So this is the terminal interface application. We have also we made a playback function here. For example, to see we see this registration. So these are registration about code 1 was, and this is our code 2. Of course, 90 kilometers an hour, the registration is very short, it's very fast. We want to show also one longer registration from Turkey. We have one longer. Was a train with many wagons of freight. So these are information, primary information for making after that post-processing function. To take displacement, to get the spectrum, to get distribution of values. These are primary data received from the sensor for the from the accelerometer system. Okay, yeah. To see if the system is working. So this is the 1 second to have also the video. So this is the sensor we placed on the contact line with this type of clamping. We can generate here low frequency, I think. Yes, at low frequency. We can generate here a high frequency of sensor. Or this kind of, they are producing high frequency. So actually, this is the simplified system of collecting data from the sensors to the interface of application. Okay, it's showing, yes. Okay, that was a little demonstration of working the sensor. Also, I have to show also this is the sensor for rails. Also, on the same interface should be in the same interface should be also the acceleration received. Yes. So that was the common point we know now, and it's very useful to propose an integrated system because the signals, the format of data we try to put to be the same. So the same interface could receive data from both types of sensor. Okay, that is what I want to show. Okay, the next presentation. You can close.
Okay, thank you, Tudor. So you're going to move on to your next presentation now.
Yeah. The next presentation is about another system designed and developed inside the NeTIRail project. It's related to the measuring current and voltage from the contact line as main parameters could show us the quality of the power supply system. So we designed a system composed by one equipment. We named the equipment for current and voltage monitoring, and one laptop. These equipment are linked to, are in the cabin of the locomotive, are linked to instrumentation transformers from the locomotive. These instrumentation transformers are used for all electrical locomotives for taking the power consumed, absorbed by the locomotive, for billing that consuming, for informing the driver, but information for taken, it's only an average. It's not detailed. To not be see the quality of the current and voltage of the power. So our system take values with very high sampling rate, about 5,000 sampling per second, to see details of this parameter. Equipment is connected to a laptop, which are running a terminal interface. So equipment is composed by two blocks: power supply module. We had to make two types of power supply modules because we met two types of main power in the locomotive. Some cases 230 volts AC, but for all the locomotives we had available only 110 volts DC. This CDM device for current and voltage monitoring was in the same design for all situations. Some differences only for making the ranges of outputs from transformers, from instrumentation transformer, to fit with our analog to digital converter. But that was only resistive adaptation. Also, after experiments, we consider also this system could be as considered as the TRL 6 level. Two sessions of experiments we made in time of the project in Slovenia and after progress in Romania. So this is the logic. This is the description of what made the system could provide quality for the energy absorbed. Also could provide this is showing that spikes could provide information about defects on the contact line, defects on the stripe of the pantograph. Also taking many registrations for the same section in time could have information to determine the wearing degree, also for helping maintenance activity. So first session in Slovenia was made in March. First we installed the system. This white box is the equipment, also connected to the laptop, and start to make registration. This equipment is connected also to that energy counter. So this is the energy counter. We made connection parallel for voltage and in series for current here. And to take the same values, the energy counter received also. For Slovenia, being direct current should have this type of shape for current. This yellow is current and white is the voltage. And many times we had a trip about 600 kilometers, 8 hours of registrations, and also all the time almost all the time we saw this type of course with some with the base. For example, here are a voltage about 3,400 volts. This is the expected shape of voltage and the current. But in some situations, we saw different. For example, in many times we saw these spikes of current, about 3,000 amperes. Luckily, these spikes are few microseconds. But in many times, and we linked showing these spikes with opening and closing of the power modules from the locomotives, also with accelerating, decelerating of the locomotive. So it's interesting to see. Could be only electromagnetic fields created in that area by the power modules of the locomotive. Another interesting aspect is about voltage. Many times, actually not about five sections, we saw this type of the voltage should be like this, but in a few times we saw pure sinus of the voltage. But that section during about 10-15 minutes. So this is the high density of we take the measurement in the narrow frame to see to see the shape. The shape is almost pure sinus of voltages overlapping the continuous component. So could be see here from 3,200 volts for about reaching about 3,070 volts. So 500 of volts alternative voltage. Here is the resistor with the terminal, and here is the post-processing. After that, we tried in the post-processing process, we tried to see the frequency. Maybe they are from the national grid, from the public grid, but the frequencies are about 300 Hz, not 50 Hz we expect. So about 500 volts alternative voltage in 300 Hz as frequency. So we think it's the deficiency of the rectified supply voltage provided in that section by the power station, because I don't know, 10, maybe 20 kilometers, we saw continuous this voltage, alternative voltage. So was one observation. The second experiment after already Romania was at the end of the March. We put also the system inside the cabin of the locomotive, and we start the application, and we saw this kind of current and voltage. For the voltage, it's good. The shape is very good, pure sinus. But the current, we saw something like this. So in many, also I will put in the playback here this continuous shape of the current here. And sometimes we saw the peaks cut it like a saturation of transformer, but the shape of the current it's a bad shape. It's not a sinus. Also have to make the same observation in the in this test after array we saw the same large amplitude of the current when power modules of the locomotives are open or closed. So this, because this is a spectrum of voltage, could be seen only the main component 50 Hz, but for the current being so discontinuities, having so discontinuities like this, we can see here beside the main component, we can see here 1, 2, and even the 3 harmonics because of discontinuity. Another parameter, another function is about cosinus phi because it's alternative energy. So cosinus phi means how part of the active power is how part of the apparent power is active power. It's a good it's a good thing here. Almost being almost one, almost all part of the apparent power is active power for supplying the locomotive. So this was the presentation for current voltage monitoring system, mostly with experiment. Thank you.
Thank you very much, Tudor. Does anybody have any questions for Tudor on that presentation? Otherwise, I suggest we move on to your final presentation, Tudor. And in this presentation, Tudor's going to talk about upgrading old interlocking systems. Thank you very much, Tudor.
Yes. So the last, maybe this system is not so difficult like the others, but it's very useful, and we'll see why. So this system is about upgrading all the interlocking systems, actually centralized electromechanical interlocking systems. All know-how for designing and developing this was provided by our colleagues from RCCF. They put in our disposition they make available their interlocking system in a Ryshnov station, and also we made tests in that location. So some about the existing situations, these interlocking systems are still used for lower density because upgrading to modern interlocking systems are very expensive, and maybe it's not working. It's not covered by the commercial revenue, by the price of tickets and so on. So they want to keep the old interlocking systems because they make work with it. But if you want to integrate new operating devices in that interlocking system, it's very, very difficult. So, for example, in the current situation, the signals and switch points are handled locally or from remote by steel cable transmission. Another problem is the status of devices of interlocking system. The status is not available. Actually, it's not available in real time. If they are suspicious about its achieved changing the status, they send a person to see and to observe which is the status. That means also including the human error. Another problem, they are not automatic data logger. Now they write on the paper the operations, the status, the events. So one example about switch point handled locally, and this is the remote control to steel cable of signal. So we design and develop one system which make monitoring in real time of all status of the interlocking system for all devices. So upgrading interlocking systems means actually to create an uniform functionality for taking the status for all devices, signals, switches, and line. These are devices attached to press signal, to entry signals, to exit signals. There looks like many, but they are only as the name and I don't know, the code is different because the functionalities, for example, for signals are the same for press signal, for entry signals, for exit signals. Also for switch here, the differences between devices are from this group and this. This is a wireless interface device for operator. It's near the cabin, and take data. It looks like a concentrator from a presented system, and take data from all these in that area of interlocking and put on the display of the operator. Also save in the file for historical analysis. So this is the idea to uniform monitoring devices from interlocking system. Auto confirmation and synchronization of the commanding activities in the centralized electromechanical systems. Also, the characteristics these devices is very important here. This system is completely autonomous and non-invasive for existing centralized electromechanical systems. This means no need, we think that no need certification, no need homologation, which are very, very hard to obtain. Because our system only monitor and send information, but the decision is still in hands of the station operator. We make only monitoring and inform the staff. Also wireless communication, total autonomy. So, one of the important advantage is increasing the interaction between operator and installation, because now the operator has in real time the information about the status of the system. Also, it's created in autonomous mode the database of all operations and events. That means increasing the operator responsibility, because now all events are known on our space. The strategy of validating the system, practically, we installed the devices, for example, for signals, and the operator sends commands to the signal, knowing commands, and we saw the response from our system about changing the status of that signal. The solution for signals is like this. Here it's the device, one interface, one resistive interface, which provides five levels of voltage for analog to digital converter with distant signification. Only element on position 1 and element on position 2 are usable, are useful. The other three situations are for taking the status of our system to see if it's a cable discontinuity or shortcut, or they are changing position from position 1 to position 2. So it's for redundancy, their redundancy status, but to be safety and to be confident to the working of the system. For example, here it's the pole we tested for signals interface. Here is the interface, the resistive interface I show. These are here. We use the switches and the magnet for switches. The validation of the solution for signals was actually to send commands and to receive, with no errors, to receive changing of the status of the signal. For the switches, autonomous switches, which are in few locations on SSDF, it's not possible to see with our sense of our resistive interface. It's not possible to see the status because the tolerance is very low. So they are used for detecting the status of the switches. They are used one device, ALP319, provided manufactured by the Siemens, and they are using also by SSTF and also by the national company of railway. We connected with our resistive interface to this sensor, which looks like this. This is the ALP319, and inside the box, they are provided some outputs with this contact. We put our resistors here, and luckily of course, with other values of resistors, we get the same 5 interval, like for signal. These are few images about connecting. This is the inside of the sensor from Siemens. We put our interface here, connected to this contact, and after that, we change the status from here. We change the status of the switch, and we register the result. We register the responses from this our system. This is the concentrator. We register here to interface the changing of the status, and we wanted and we managed to change all the status and to see all this changing. So no message about status of ALP319 was filled. So that was the presentation for upgrading interlocking system.
Thank you very much, Judah. Okay,
can I show? I forgot. Can I show the interface for current and voltage monitoring? One file register.
Yes.
Yes. Okay. Start at the PDM. I forgot to show. So this is the interface for presented current and voltage monitoring. I can show only some files registered here. So this is the file with large ripple, large voltage. You saw here. This is the current. You saw some spike. Yes, and this is the current. Yes, these spikes are appearing on the commuting power modules on the locomotive. And this is voltage, alternative voltage on Slovenia. Actually, many times, almost all the time, we saw this type, not this type of shape. And I marked here. Yes, almost the time, many hours we registered this kind of voltage and current. Not I showed earlier. So these are proof about our experiment. Also for after something interesting here. Let's make. So this is a bed shape I want to show about the current. When it's changing, that means input, that means more consuming or less consuming of the power. Yes, this is a bed shape of sinus with changing the amplitude, changing the shape, and that provoked in relative with the voltage, which are very, very clear signs. Okay, this I wanted to show. Thank you very much.
Okay, thank you very much, Tudor. Does anybody have any final questions for Tudor or any of the other presenters? If not, I just want to leave you with my contact details. So you should be able to see on screen now my email address. And also to remind you that this afternoon we have another webinar about the GIS web-based application that's developed under Work Package 6. So I've put the link on screen for you, but I've also put it in the chat section so that you can copy and paste it if you need the link. You can also find it on Twitter. If you just search on Twitter for NeTIRail, you can find the link to that webinar this afternoon. Okay, thank you very much everybody for joining us. And as I say, if you want any more information or you have questions that you haven't raised today, please send me an email and I will pass your questions on to the appropriate people. Thank you very much, everyone, and goodbye. Thank you.
Right. Thank you, John, for the organization. We keep in touch. Bye-bye.
Okay. Thanks, Alfredo. Bye-bye.
Thanks a lot. Thanks a lot. Bye.
Thank you.
Bye.
Bye.